morning, everyone. How are you going? Have you enjoyed the conference? Yeah, you're not too tired. End of a long week, I bet. So thank you so much for choosing to attend this session. I really do appreciate it. Looking at my fellow speakers in this slot, it does appear to be all killer, no filler. But rest assured, and this is coming from a really pure, genuine place of self-interest, but I can assure you that you have made an excellent choice. So we do have quite a lot to get through today, so I am just going to get straight stuck in. So quick intro, my name's Adele Carpenter. I'm a software engineer at Trifork Amsterdam. Most of my day I do spend building and maintaining Kotlin and Java applications for the educational sector, although more and more lately you will find me try not to cause too much damage with React in the front end. And as the title of this talk suggests, this is part 2 of a topic that I have spoken about before. And so has anyone here seen part 1 of this talk, either in person or online? A couple. Excellent. Great. Thank you so much. Welcome back. So rest assured, I'm not going to repeat myself. So part 1 and 2 are completely standalone. But if you haven't seen part 1, then you won't be playing catch up at all. So while I am really proud of part 1 of this talk, perhaps I was a little bit too ruthless in the detail that I did leave out to tell a nice story in a digestible way. So I'm going to revisit that choice, and I'm going to provide a little bit more history and context to civil aviation, the study of aviation disasters, and of course what we can learn from that as software professionals. So first up, just a little quick review of the first 50 or so years of aviation, and this always boggles my mind that 120 years ago we were simple ground dwellers, and well, now we are simple ground dwellers with flying machines. And I don't want to spend too long on this, so buckle up, and I'm going to keep the pace really, really high. So this is a bare bones timeline from 1903 to 1950 or so, and I'm going to run you through it real quick. So aviation, as we know, it started with the Wright brothers in 1903 with the first man-controlled flight. And just over 10 years later, when World War I rolled around, developments accelerated to match the new technology to the requirements of the battlefields. Between World War I and II, there was space for a bit of fun, and we saw the first airlines, daily passenger routes, air shows, and transoceanic flights. But when the fun stopped again with World War II, developments in aviation kept accelerating. Most of the developments, of course, were around air-based weaponry, but we did see more general improvements, such as improvements in manufacturing processes and the development of the jet engine. Now, after the war, humanity did have the space again to focus on commercial aviation, and we saw air traffic grow by about 20% per year. So by the time we get to this point, in the late 1940s, we have a paradigm-shifting technology whose early development was catalysed by not one, but 2 world wars. And then this was followed up by a rapid period of adoption and growth in the civilian sector. So what do you think is going to happen at this point? Disaster, of course. So here is a summary of the causal factors of plane crashes from 1950 until 2019. I got this table from a website creatively titled planecrashinfo.com. I debated on whether or not to recreate this table in a more aesthetic and less grainy way, but I actually kind of love it. I know that it looks like it hasn't been updated since 1996, but the website is actively administered, and the latest crash in the database is actually from just a few weeks ago. So aviation geeks are really not that different from dev geeks. We, the dev geeks, might have the slicker online tools, but the level of detail, care, precision, and obsession is the same on both sides. The Venn diagram of both communities is basically a circle. And just a quick note before we do dive into the numbers, be aware that this covers civil aviation only and fatal crashes where at least 2 people have died. So the military is not included at all here. So now that you've had a little bit of time to digest it, even with me up here making bad jokes, I do hope that something has already leapt out to you, which is that over the decades, the most common cause of fatal air crashes is pilot error. You may have also noticed that the breakdown by these 4 broad causes is relatively consistent, although we can see that mechanical causes have reduced since the 1950s and 60s. But worryingly, if we look a little bit closer, we might want to infer a jump in the number of crashes caused by pilot error in the 2010s. Now, later I will discuss a case study that hints at to why, but for now I want to take a look at the actual numbers of the crashes. Because if we look at the actual numbers rather than the percentages, it tells a different and a more hopeful story. Again, with the beautiful formatting courtesy of the source website. So here we can see a peak of crashes in the 1970s at 230, with pretty remarkable attenuation after that. And this drops every decade until the 2010s, until we're left with 49 fatal crashes, and 28 of them due to pilot error. Now, please bear with me for another 30 seconds as we do paint the final bit of the picture here. We can see the global fatalities per million passengers consistently dropping for decades. And we're now hovering at around 1 death per 10 million passengers. So climate issues aside, aviation is an incredibly safe mode of travel, and it has only trended towards safer. And this is an engineering success story that I think we can learn a lot from. Because one thing that I really appreciate about the aviation industry is the deep understanding that there is rarely one cause for something. And if you do read the final air crash investigation reports, and trust me, I have read more of these than I do care to remember, you will find that there is a list of causal factors and a list of contributing factors for a crash. Disaster is not something that just spontaneously happens. Often, many systems, people, process, and mechanical, have had to break down. So with that in mind, there was one big change in the late 1970s and early 80s that did drastically reduce the number of crashes attributable to pilot error. And that was the expedited introduction of crew resource management after the United Airways Flight 173 in 1978. Now, I do cover that crash in more detail in part 1 of this talk, and you can check it out online if you're interested. But in short, while working on resolving an issue with the landing gear, the captain was unaware that the plane was running out of fuel. And a causal factor of the crash was a breakdown of communication in the cockpit. The captain didn't ask, nor did the co-pilots assertively communicate the severity of the fuel situation. And in the end, they did run out of fuel and 10 people lost their lives. So crew resource management effectively teaches airlines how to make effective use of the resources available them to ensure the safety and efficiency of flights. And this includes equipment, procedures, and people, both inside and outside of the cockpit. And originally this training was introduced just for pilots, but now is an important part of training for the cabin and for the ground crew as well. And this has really been a big driver of the reduction of crashes related to pilot error. So in the 2000s, we saw another drop in crashes attributable to pilot error as CRM was expanded into emerging aviation markets. And the 1990s and the 2000s also saw wider adoption of fly-by-wire technology and flying automation, accompanied by enhanced protections and warning systems. So if you consider this in the context of continuous improvements to maintenance procedures, training, and regulatory oversight, this really did lead to a period of big leaps in aviation safety. Even crashes due to the weather dropped in that period, as airports and crews gained better access to meteorological data and training, and aircraft were fitted with advanced features like wind shear detection systems. And if you don't know already, wind shear is the pants browning experience of a sudden change in wind direction. So you can imagine that if you are close to the ground and you get a sudden gust of wind downwards, just how dangerous that could be. So the widespread introduction of airborne and wind shear detection alert system was a key recommendation after the crashes of Pan Am Flight 759 in 1982 and Delta Airlines Flight 191 in 1985. So in this respect, these crashes were instrumental in advancing weather-related safety in aviation. And while it certainly is true that technological advancements have been a significant driver in improving aviation safety, it would be remiss of me to gloss over the fact that this progress has brought with it significant challenges. And I think the discussion and appreciation of these challenges is where the real gnarly insights for software professionals lie. So fly-by-wire and its related systems has really opened the door to a lot of questions surrounding the pilot's role in flying the aircraft and the limitations of humans when it comes to understanding and interacting with automation. So fly-by-wire was first deployed with the F-16 in 1974, and traditionally fixed-wing aircraft are controlled by a control column or a yoke, and this yoke is mechanically connected to the flight control surfaces of the aircraft. So when the pilot pulls the boat yoke back, this is a direct input on a cable which moves the elevator up, driving the tail down and therefore the nose up. And the key point here is that there is a cable or rod running from the cockpit to the tail and the other flight control surfaces. Yet in fly-by-wire, the flight control computer accepts the pilot input to the controls and manipulates the control surface in such a way as to produce the pilot's intended results. So essentially, the flight computer acts as the middleman for the pilot's instructions, a much lighter, smarter, and opinionated middleman than traditional cables and rods, where it delivers its instructions by wire. Now, this middleman can and does provide protections to ensure that the aircraft stays within its safe flight parameters. So if the pilot is trying to pitch the nose so far up that the plane will lose lift and enter a stall, the computer will be like, nah, I don't reckon, and make a much smaller and safer adjustment to the flight control surfaces. So in the words of the early F-16 pilots, you don't fly an F-16, an F-16 flies you. Now, moving back into the commercial realm, 1988 saw the launch of the Airbus A320, which was the first airliner with fully digital fly-by-wire controls. It was also a key moment in what has become somewhat diverging philosophies of Airbus and Boeing with respect to automation. So Airbus's stance is that automation should allow the pilot to use the safe flight envelope to its fullest extent. The flight envelope is basically the safe operating limits of the aircraft, although this can vary based on weight, speed, and altitude, amongst other things. So at a certain weight and speed, for an example, there is a safe range of altitude. And this is also where the English expression pushing the envelope comes from, meaning to push the limits of a situation. And the flight computers on Airbus follow a series of laws that offer various layers of protection. And a protection is basically a nah, I don't reckon, response from the flight computer. And these laws are called normal, alternate, and direct law. And in normal law, you have the most protections, and in direct law, you have the least. And I think that this is really a telling design decision from Airbus, that it's actually not possible for the pilot to decide which law they want to operate under. This is actually always determined by the aircraft. And the only way that I can think to explain this is that Airbus takes a computer-centric approach. Boeing, on the other hand, has traditionally taken a much more pilot-centric approach. They did in 1994 introduce the 777, which is fly-by-wire, and later the 787 or Dreamliner. However, their highest-selling aircraft, the 737, decidedly has mechanical controls. And a quick nod rather to the elephant in the room named Max, because we have seen some deviation from that approach recently with the introduction of MCAS in the 737 MAX 8. But it is a little bit of a special case, and that is worthy of its own talk. And you're in luck, because there actually is a talk about the MAX 8 by a man named Kyle Kotowick. I saw it earlier this year in this building, actually, and I do highly recommend it. And he's been giving that talk for a little while now, so you should be able to find that online. In any case, I am not in a position to make a claim about which philosophy is better, whether that be pilot-centric or computer-centric, if one is at all. I just find it interesting that the two largest aircraft manufacturers, despite traditionally putting the same priority on aviation safety, have taken two different approaches to achieving it. So begs the question, what are the appropriate roles of human and machine when it comes to machine-assisted decision-making? And we are facing this question right now with the introduction of AI assistance tools like ChatGPT and Copilot. And we've seen a lot of talks at this conference about that topic. And there's one crash that I think sums up these issues quite well, and I will be sharing that with you now in a storytelling format. I do warn you that it is quite heavy, and it also is relatively recent. This is also the heaviest part of the talk, but it is necessary as it does set us up for a nice discussion afterwards. So just to break the suspense a little bit while I take a sip of water, the flight is Air France 447, which crashed into the Atlantic Ocean on June 1st, 2009, as it was returning to Paris from Rio de Janeiro. And just at this point, I'll ask you to prepare your eyes a little bit, because we are just about to enter dark mode. Here we go. So it's June 1st, 2009. Air France first officers Daniel Robert and Pierre-Cédric Bonin are in the cockpit of the Airbus A330 over the mid-Atlantic Ocean. Bonin, the less experienced of the two pilots, is the pilot flying in the right-hand seat. Robert is the pilot not flying in the left-hand seat, the captain's seat. So wait, where's the captain, you might wonder? Well, as this is a 14-hour flight from Rio to Paris, the allowed duty time for pilots of 10 hours will be exceeded. So in order to complete the flight and manage the fatigue of the crew, the three pilots rotate so that some of them, so one can take some rest and the others can remain alert while they're in the cockpit. So Captain Dubois has just stepped away for his rest, and so nothing is out of the ordinary. However, Bonin is feeling a little uneasy. He is flying through the Intertropical Convergence Zone in June, and as is common at this time of the year, he is experiencing some light turbulence as he flies through a layer of cloud. And he had discussed the weather with Captain Dubois just before he took his rest. He'd proposed a couple of small adjustments they could make to the flight path to potentially avoid the worst of it. But Captain Dubois was not particularly concerned, and the proposed adjustments also do carry some risk. Bonin and Robert notice some ice crystals in the cloud layer and turn on the anti-icing system. Less than 3 minutes later, an alarm sounds. The autopilot has disconnected. I have the controls, says Bonin. Robert confirms. The plane rolls from side to side a little as Bonin settles into flying the plane manually. He pitches the nose up. We don't have a good indication of speed, he says. The autopilot has disengaged because the flight computer can't make sense of the conflicting data that it is getting. The data is bad because the airspeed sensors are clogged with ice crystals. Alternate law, protection's low, says Robert. In alternate law, there is still some support from the flight computer, but critically, there is no anti-stall protection. Not long after Bonin takes the controls, the stall warning sounds. The stall warning is designed to be as intrusive as possible. So think of the loudest crickets you've ever heard and multiply it by 10, and that's on top of a continuous C chord master, as well as multiple visual alerts. This is pure sensory overload. Robert adds what must be overwhelming noise in the cockpit. Watch your speed, watch your speed. Okay, I'm going back down, replies Bonin. According to all three, you're going up, so go back down. Bonin reduces his nose up input and thrust, and the stall warning temporarily stops, although there are still several other warnings demanding their attention. The pilots have control of the plane again, yet confusion remains. Unbeknownst to them, the airspeed sensors are now ice-free and all of the avionics are functioning normally again, although there is still some curious behaviour from some instruments. They still don't have a full grasp of the situation. Robert focuses his attention on summoning the captain. Damn it, where is he? The stall warning starts again. I'm in toga, right? Says Bonin. Toga is short for take off and go around. This setting provides the maximum thrust needed for the plane to take off with the nose pitched up. It's designed to be applied at lower altitude where the air is heavier. And this statement hints at that Bonin, to quote the investigation report directly, has built an erroneous representation of the aeroplane's flight model. And the fact that his actions are not resolving the warning deepens his mistrust at what the aeroplane is telling him. And he's further emboldened by the fact that the A330 does carry robust anti-stall features. Anti-stall features that are not available to him in the current flight state of alternate law. I don't have control of the aeroplane anymore, exclaims Bonin. Control to the left, asserts Robert. 8 seconds later, Captain Dubois enters the cockpit and takes a seat behind Robert and Bonin. What are you doing? What's happening? I don't know what's happening, says Robert. We're losing control of the aeroplane, confirms Bonin. Over the next 2.5 minutes, the three pilots try to understand and resolve the situation. Captain Dubois recognizes that they are in a stall, and Robert pushes the nose down to try and gain airflow over the wings. More airflow, more lift. But they cannot regain control of the aeroplane. When they get dangerously close to the sea, Robert reverses inputs by pulling back and says, climb, 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 climb. Chillingly, Bonin responds, but I've been nose up for a while. Captain Dubois pleads, no, don't climb. Give the controls to me, says Robert. Go ahead, you have the controls. We're still in toga, yeah? Replies Bonin. Robert spends the next 35 seconds trying to recover the aeroplane, but it is far too late. Moments later, Bonin exclaims, we're going to crash, this can't be true. And the cockpit voice recording ends, along with 228 lives. I read this transcript of this flight many times, and it still sends like a chill down my spine every time I read it. For obvious reasons, the real recording hasn't been released, but I can just imagine the investigators just sitting there listening to it dumbfounded. And it is easy to blame the pilots for this crash, and many people have, including the press and the courts. And to say that they are not at all responsible for the crash would also be incorrect. But as someone who did not lose a loved one in this disaster, I have the luxury of being able to avoid the blame game, and I can instead focus on what we can learn. And do you see here in the subtitle the implication that the pilots were shirking their responsibilities and sleeping on the job? A sleep mandated by safety requirements? This is classic tabloid journalism. Anyway, I do digress. Air France 447 highlights something that I don't think we think about enough as software professionals, and that is how humans interact with complex systems, particularly those that have a lot of redundancy. Because there's a tendency to think that outside of cost considerations, more redundancy is better. And in safety critical systems in particular, you're willing to take on those extra costs in order to have that extra safety or fallback. And even in non-safety critical systems, there is an expected level of redundancy. The classic examples being backups and having your application running in multiple regions or data centers, or running your database or message broker as a cluster. Indeed, in my team at Trifork, we run our own cluster of 3 nodes of our message broker, RabbitMQ. 3, of course, being the magical minimum number for redundancy. And recently we encountered an issue that caught us a little bit by surprise and resulted in 8 minutes of downtime of our main application during a busy period. So show of hands if you're using or have used RabbitMQ in production. Yeah, a few of you. Okay, so see if you can figure out what's going to happen while I tell this story. So just like you'd see in the cockpit, we started receiving alerts about an unexpected state. We had a growing number of messages in 2 of our production message queues, in addition to disks that were getting dangerously full. Now, the number of messages in each queue was around 600,000 each, which was high, but was not unexpected during a busy time. However, the rapidly shrinking disk space was concerning, and the message throughput was slow. So we decided that a low-risk first course of action would be to restart one of the affected applications listening on one of the queues. Unfortunately, that did not resolve our issue. So after some back and forth in the team, and with the disk getting ever more full, we decided to take a secondary RabbitMQ server offline and bring it back with extended disk space. And at first, this seemed to go really well. We took the node offline without any problems, and the application was still limping along, serving requests with fewer nodes. But there was a key part of this redundancy model that we didn't understand. And because the queues were very large, in total over 1 million messages, when we reattached the node to the cluster, the node started to sync itself to the queue, basically stopping time while it copied 1 million messages. And all we could do was wait. So during what felt like the longest 8 minutes of my life, no messages could be consumed at all, and as such, our main application was unavailable to our users. So those with the Rabbit experience, did you guess this correctly or know this more accurately? Okay. So no one. Okay, so we're not alone here. So I think you can see the point I'm trying to make. So this isn't a perfect example, but it does show the perils of interacting with complexity and redundancy under pressure. Probably someone on the team should have known about the sync time on such a big queue. But once set up, the queue just kind of works. So back to the Airbus. Here is a schematic of the systems involved in providing the aerodynamic and inertial parameter data to the pilots of an A330. So ADIRU is short for Air Data Inertial Reference Unit. And you might recall from the first part of the Air France 447 story, the autopilot disconnected due to conflicting airspeed data. The air data part of the ADIRU is most notably responsible for providing the calibrated airspeed and Mach data to the pilots. And if you're thinking, wait, isn't Mach speed too? Well, you're right. Mach is presented as a fraction of the speed of sound, and calibrated airspeed is presented in knots. Now, I am oversimplifying here, but above about 28,000 feet, Mach typically becomes the more important measure of airspeed. And the inertial part of the ADIRU provides data such as the ground speed and attitude or pitch, so the number of degrees the nose is pitched up relative to the ground. So you can see here on the left and right side the physical sensors that provide the data to the ADIRUs, and without getting, bogged down in specifics, the airspeed data is calculated from static and total air pressure. And there are 6 static air pressure sensors on an A330. The total air pressure is measured by something called a pitot probe, which is a small tube that sticks out the side of the fuselage. And the A330 has 3 pitot probes circled in green here. And you can see here that the data from Pitot 1 feeds the captain's flight display, Pitot 2 feeds the co-pilots, and Pitot 3 feeds a standby flight display. And you can also see something here called ISIS, which is an unfortunate name, I know, especially on an aeroplane. And this is the Integrated Standby Instrument System. And this is designed to serve as a backup in case of the failure of one of the standard flight displays. So you can forget turtles. This is redundancies all the way down. So we have redundancy of data, given that we have multiple sensors measuring the same thing. We have static redundancy of the 3 ADRUs, where an error in one system can be outvoted by the 2 other systems. We have the redundancy on top of those 3 flight display systems with an external computer system that integrates information from a variety of sources. And now if you're feeling overwhelmed, confused, unsure, or simply bored right now, then you already understand the point that I'm trying to make. Redundant systems do not operate in isolation. When they work, they're great, and when they fail hard in unexpected ways. And often what you'll find at the other end are some humans under immense pressure to not only figure out what is happening, but also to save the day. In the case of Air France 447, the cascade of unfortunate events started with the loss of reliable airspeed information due to the pitot tubes icing over in the absence of the captain. The autopilot could not make sense of the conflicting airspeed data it was getting, so it disconnected. Let the humans figure it out. The aeroplane displayed an abundance of alerts and messages to the co-pilots who had not encountered this situation before, not even in the simulator. To make matters worse, many of those messages were about the consequences of the problem rather than about the origin of the problem. And unable to make sense of the data being presented to them, the pilots failed to diagnose the situation correctly and apply the appropriate checklist. Under stress and possibly suffering from the startle effect and possibly reacting to the intermittent appearance of the crossbars on his display, Bonin pitched the nose up. He had little practice manually flying the plane at altitude and was used of the A330's anti-stall protections, but the anti-stall protection was gone once the flight computer shifted into alternate law. A fact that Bonin was expected to recall within seconds. In fact, the civil aviation regulator of the US, the FAA, assumes that pilots can recall such pertinent information within 3 seconds. Tragically, the attempts of Robert to push the nose down to gain speed over the wings and recover the stall proved futile. Due to the design of the cockpit and the controls and the fact that it was dark, Robert could not see that Bonin's side stick was being pulled back. So the conflicting input of the pilots, one nose up and one nose down, effectively cancelled each other out and added even more confusion to the situation. So when Bonin finally exclaims, "But I've been nose up for a while," the penny finally dropped, but it was far too late. And Air France 447 is basically the poster child for automation gone wrong, and the media certainly had a field day with this narrative. But the more interesting and less tabloid-worthy discussion for me is, how do we design more human-centric systems in a digital world? Now, not just for users, but for ourselves as developers. Because I really dislike this approach of, oh, well, if the unexpected happens, say, I don't know, and hand it back to the users. Maybe you can get away with that with simple systems, but as a system gets a lot more complex, you're actually demanding a lot from your users. So at best, your user gets annoyed, but does in fact try again later. And at worst, you have a plane falling out of the sky. Somewhere in the middle, there's me holding my breath for 8 minutes while a new node syncs to a queue of a million messages while it reconnects to the cluster. Somewhere next to me, there's you having a mini meltdown because your Slack is blowing up and your exquisite dashboards have disintegrated into an amber and red mess. And in the corner, there's Pete having a great time with his headphones on and his alerts muted because the alerts don't usually mean anything anyway. So in order to start thinking about human-centric design, you've got to understand some simple features of humanity, or depending on who you ask, bugs of humanity. And aviation has certainly encountered most of them. So first is that we have a limited working memory. So are you already familiar with the concept of cognitive load? Yeah, a few of you, great. So just quickly, cognitive load refers to how much of our working memory is required for a task. Now, you may have heard that your working memory can hold 5 to 9 chunks of information, but the number that actually shocked me is that we can really only work on 2 to 4 of those chunks at once. But the cool part of this is that this limit applies to novel information only, so not information that's already in our long-term memory. So for pilots, this highlights even further the importance of relevant training and experience to free up as much working memory as possible for truly novel information. And as developers, we can strive to make the way that people interact with our system as consistent as possible. So consistency over correctness is not a dead concept. Copa Airlines Flight 201 highlights the importance of consistency over correctness in human-centric design even further. In 1992, a Boeing 737 crashed in Darien Gap, a region of almost impenetrable jungle in Panama. Despite the immense challenges of the terrain, investigators were able to piece together the flight data recorder and collect the bulk of the wreckage. A key piece of the puzzle was the data from the captain's vertical gyro. Now, the gyro is the data source for the attitude indicator, shown here, which is the instrument I think most people associate with flying. So this one here is similar to the one on Copa 201, and it shows the plane in relation to the horizon, and it's very, very difficult to fly without it. And given that it is so critical, some smart engineers built some redundancy in. So similar to this airspeed that we saw on the A330, there is a gyro on the captain's side that feeds the captain's display and one on the right side that feeds the co-pilot's display. There's also an auxiliary gyro that feeds a standby display. And if you identify an issue with one of the gyros, for example, the captain's gyro, there's a switch where you can set the data for both displays to the co-pilot's gyro, so like this. So also similar to what we saw with Air France 447, Flight 201 starts receiving bad data, which causes the autopilot to disconnect. This time, the faulty data source is from the captain's gyro. So in the dark, the pilots need to manage flying the plane with a broken attitude indicator. And the investigators can only be shocked as the flight data recorder tells a terrifying story of the pilots repeatedly reacting to bad data until eventually they roll the plane out of the sky. Why didn't they just switch the data source? So here's how the switch appeared when it was pulled from the wreckage. It says both on Fiji 1 or vertical gyro 1. So this means that the pilots had identified that they were getting bad data, but then they pointed both displays to the bad data source. What were they thinking? Now let me show you the same switch as installed on the simulator the pilots were trained on. So putting aside the fact that it's a different style of switch altogether, in the simulator, left means give the captain the auxiliary data, and in the plane, left means switch the co-pilot to the captain's bad data source. And so this is deadly UX if you are ever going to see it. And it's the most extreme example you're ever going to see of consistency over correctness. So moving on to the second bug of humanity, which is that we have a blind spot for our assumptions. So in 1989, British Midlands Flight 92 crashed while attempting an emergency landing. The first sign of trouble in the cockpit was a loud pounding noise and a severe vibration. In the cabin, smoke poured in, and some passengers could see sparks coming from the left engine. And whilst the pilots were very experienced on this aircraft type, the 737, they only had 76 hours combined on this version, the 737-400. In previous versions of the 737, the right air conditioning system receives what's called bleed air from the right engine as it supplies air to the cabin. And the left does the same for the cockpit. However, in this newer version of the aeroplane, the air from the left and right is mixed as it re-enters the aeroplane. So the captain, relying on his experience, sensed the smoke coming forward from the cabin and assumed that the fault was with the right engine. Now, based on this shared assumption, he and the co-pilot powered down the engine on the right. Now, unfortunately, as bad luck would have it, at this exact moment, the auto throttle disengaged, reducing fuel flow to the left engine. And as a result, the fire weakened and the smell of smoke subsided, which seemed to confirm to the pilots that they had taken the right course of action. But when they start the approach for the emergency landing, they increase the thrust, growing the fire to the extent that it kills the damaged left engine entirely. And by this point, they are just traveling far too slowly to restart the good engine, and they crash right next to the motorway. Now, I do have a little bit more to say about the Midlands crash, but before I do, I want to introduce the next bug of humanity we will be discussing today, which is we do irrational things. So despite heavy protest to the contrary, rational people do irrational things. Yes, even developers, and yes, especially users. So British Midlands was one of two crashes in Britain in the 80s that were pivotal in improving the survival rate of survivable crashes. And no, not because everyone got a lecture on verifying their assumptions before acting, although that would be useful for most people. I'm sure you've already thought of a colleague that needs that lecture. So of the 126 passenger and crew on board Midlands Flight 92, 79 people survived, with 74 of them suffering injuries. And by examining the injuries and the aircraft, a number of recommendations were made relating to the aircraft itself, such as improvements to seat floor and overhead bin design. There are also changes made to the recommended brace position and the restraints of young children. However, the survivors of Midland's crash had already benefited from the 1984 Manchester airport disaster, which happened only 4 years earlier. In this crash, engine failure during takeoff generated a fire. The takeoff was aborted and the captain ordered an evacuation. Of the 137 passengers and crew on that flight, 55 died, mostly from smoke inhalation, as they attempted to rush, climb, fight, and squeeze their way to the emergency exits. And the Manchester airport disaster forced aircraft manufacturers to consider the behaviour of a group of humans facing death, behaviour which in most contexts would be completely irrational. So these changes included making it easier to find the exit by installing the strip lighting in the aisles, creating more space for exiting the aircraft by removing a seat at the overwing exit and by widening the entry to the galley. So the galley is the little kitchen on the airplane where the terrible coffee is made. Also installing fire suppression systems in the cabin and the introduction of less flammable materials for things like seat cushions and carpets. So only a few small changes. Implement that in a weekend. For the airlines, changes included spreading crew of different experience levels throughout the cabin and pre-flight safety briefing for passengers sitting in the exit row. So digging down to a more individual level, rational choices are often driven by bias, emotion, and stress. In the final report of Air France 447, investigators mentioned that the crew acted irrationally in response to the anti-stall warning, probably due to the startle effect. Ongoing training is often repetitive and well known to the crews, blunting their ability to react in a measured way to the truly unexpected. But I think the bigger point here is the role of stress in your users' behavior. So have a think about the stress that your users could be experiencing. For example, noisy environments or a poor internet connection. How can you make it easier for them to interact with your application under those circumstances? The last bug/feature of humanity I would like to mention today is simply that we get used to things. As was the case with Pete and his muted alerts, repeat applications of a stimulus tend to result in a decreased response. In psychology, this is called habituation. So if the alerting is too eager, eventually you will start to ignore the alerts, putting you in the same position as if you had no alerts. Another manifestation of getting used to things is simply going through the motion. So even if something does have a high risk of going wrong, if you do it enough, you can become complacent. So in 1988, Delta Airlines Flight 1141 crashed shortly after takeoff because the flaps were not deployed. So these things here. So as you can see, the flaps extend out the back of the wing during takeoff and landing. So this extends the surface area of the wing so that it can generate more lift when the plane is moving more slowly. And it's a pretty crucial part of the takeoff procedure. So in the cockpit voice recording, the pilots can be heard chatting along, while they are going through the pre-flight checklist. And while both pilots do announce the deployment of the flaps, the sound of the flap lever actually being moved in position cannot be heard in the background. An examination of the wreckage confirms this finding. However, the pilots who had survived, they were in pure disbelief. They were absolutely certain that they had deployed the flaps. And the absolute kicker in this case is that the aircraft, the Boeing 727, did have a takeoff warning system installed. Now, this system provides an audible warning to the pilots that the aircraft is not ready for takeoff. It literally yells at you if you try to take off without the flaps deployed. In this case, the switch for that operated the takeoff warning system had been modified so as to prevent nuisance activations during aircraft taxiing. So I think we have just enough time for this final story. We might go 1 minute over. I think you can handle it. So I have a confession to make. I know I promised you a discussion of project failures and wrong incentives. And when I promised you that, I did have a particular story in mind. So imagine my surprise when I found out that it isn't true. So this is the de Valhalland Comet, the world's first commercial passenger jet. And if you ask the internet why are aeroplane windows round, you'll be generally met with a statement along the lines of, well, we tried that with the Comet and it crashed because of stress at the corners and of the square windows. So let's zoom in a bit so you can see those square windows. And the story gets better. And this is why I want to share it with you, because apparently it was the manager that suggested that the windows be square so as to separate air travel from, the round portholes of sea travel. And so because the ego-driven manager said so, and with incentives in place that favoured not rocking the boat over prioritising safety, we got square windows and disaster. All entirely believable and relatable, but all mostly untrue. The Comet did unfortunately suffer from structural fatigue issues in the fuselage, but as you know already, there's rarely one cause for a failure, and this case, of course, is no different. But if you do go back to a choice zero, so to speak, it was the decision to use a specific type of engine, which turned out to be incredibly underpowered. And this required the design of an ultralight fuselage, which proved susceptible to structural fatigue, which is an issue that was not well understood at the time. So now we are at the point where I make the closing remarks, and I do put what I've said today in a neat little package. So this is the part where I can give you the list of takeaways that you can take your picture of. However, before I do that, I do want to acknowledge that I've probably provided you with more questions than answers, and that is totally fine by me. So I want you to take this list of takeaways I'm about to provide with a grain of salt. And if there's something else that resonated with you, please just take that and run with it. And if you see me outside after the session, I would love to hear your take. But for now, here's what I hope you got out of this session. First, rapid adoption of a new technology will always have problems, but it's the way that we approach these problems that matters. As a technology matures, the human element becomes even more important. Focus shifts from making the technology better to understanding the users better. More redundancy is not always better. It's important to weigh the extra safety and reliability of the system itself with the cognitive load put on the users to understand and interact with the system. Users is a wider definition than you think. Start thinking of yourself as a user of the system you build and maintain and see where that gets you. Lastly, the humans that interact with your system have significant shortcomings simply because we are human. Learn to work with it, not against it. My name is Adele, and thank you so much for your time. Thank you. Please don't forget to rate this session. I know you're probably a little bit fatigued from giving reviews, but this is really useful. We do read that feedback. It can make or break my speaking career, so really appreciate it. Thank you.